Hey friends, hello, welcome back to the channel. Very happy to see you again. Today's topic is the formation of the T wave. We have learned the formation of the P wave QRS complex. Now it is the turn of the T wave. Let's start. The questions regarding the T wave are these two. The first question is when the activation of the ventricles produces a spiky QRS complex, why the T wave is not similar to the QRS complex? Why T wave is similar to the P wave, which is a smooth rounded shape wave? The second question is when the QRS complex is the activation of the ventricles, why the opposite phenomenon, the repolarization, is again recorded in the direction same as the QRS complex? So these are two very important questions. Let's try to answer them one by one. If this is the epicardium and this is the endocardium, then the conduction system lies over here in the subendocardial area. So it's not in this type of ring form. What I'm trying to tell, just try to imagine the thing. It lies here and travels in this way. The thing that I am trying to tell you is that the conduction system is located in the subendocardial area. So the right bundle branch, the left bundle branch, and its branches, the anterior and posterior left bundle branches, these are subendocardial structures. Looking at the thickness of the myocardium, if this is the blood pool, the RBCs, this is the endocardium, here is the epicardium. The activation first reaches the endocardial areas. Let's draw activation like this. And then by the spatial propagation of the activation wavefront, the activation happens this way from the endocardium towards the epicardium. In general, cardiomyocytes which are located here in the near to the endocardial layer, they are activated first, and the cardiomyocytes which are located here, which are distant, they are activated later. And the very important thing, the very important difference is that when the activation occurs, it is the cardiomyocyte which then activates its neighbor cardiomyocyte, which then subsequently activates its neighbor cardiomyocyte. So it is one cardiomyocyte influencing the other cardiomyocyte, and that in turn influence the other cardiomyocytes. But mind you, the repolarization process, it is not like that. It is fundamentally different. When one cardiomyocyte activates the other cardiomyocytes and it in turn activates its other cardiomyocyte, this is the depolarization. But the very important fact is that this cardiomyocyte which was activated at this time, we'll call it as 0 seconds or in fact millisecond, the activation potential has begun there, which was at 0 activation process. The activation potential has begun here. Then the plateau phase would come in this cardiomyocyte, and then the repolarization will occur. Correct. So let's draw in a better way. This is the cardiomyocyte. This is the very subsequent cardiomyocyte. This is the very subsequent cardiomyocyte. Depolarization occur at 0 millisecond, 10 millisecond, 20 millisecond. The activation is passed on. So at 0, the activation goes up like this. At 10, the activation goes here. The activation goes here. So all of them, they are in a plateau phase. They are in their plateau phase. They are in their plateau phase like this. So irrespective of anything else, once this cardiomyocyte gets activated, the depolarization happens, the plateau phase will come, and the repolarization phase will occur. So it does not depend on the neighboring cardiomyocyte. The activation of this second cardiomyocyte depends when it gets activation from this first cardiomyocyte. But its repolarization, it does not depend on what is happening in the neighbors. It depends on its own milieu, transmembrane potential. So once it has got depolarization, the plateau will occur and the repolarization will occur. So this is bound to happen. One important fact is that the plateau phase and the repolarization for cardiomyocytes of the endocardium, for example, if it is this long, the same for the epicardial cell, which starts slightly later, then the plateau phase comes, it is shorter, which is the epicardial. So looking at this diagram, you can get very important information. The action potential duration for the endocardial cardiomyocytes is longer, whereas the action potential of the subepicardial cells is shorter in duration. Correct? And this duration is shorter, this duration is longer. So due to this, what happens is the endocardial cells get activated, it is taken to the epicardial cells towards the border in this direction. But one would expect that okay, it started here and ended here, so these cells will first repolarize and then these cells would repolarize later, and the repolarization will happen again from the endocardium towards the epicardium. But it does not happen like that. What actually happens is, even though this cardiomyocyte is getting activation at a later point in time, its action potential lasts for a shorter duration. The plateau phase is shorter, and so the repolarization of this subepicardial or epicardial cardiomyocytes is shorter. So actually they first repolarize, and subsequently its neighbor repolarizes, then its neighbor repolarizes, and at the last the subendocardial cells repolarize. It's not that this cell causes repolarization of the neighboring cells. It's just that the timing of the action potential of each and every cardiomyocyte is such that the endocardial cells, they have a longer duration of action potential, whereas the epicardial cells have a shorter duration of action potential. And so even though they get activation at a later time, their repolarization happens uh, earlier as compared to the subendocardial cardiomyocytes. For this cardiomyocyte, the action potential will be slightly longer than this one. For this, it will be slightly longer than this one, and for this, it will be slightly longer, and this will be the longest action potential. So, in the sum game, what happens is that the repolarization that happens from the epicardium, from here, the epicardium, from here towards this side. So the depolarization wavefront, which was going from here endocardium towards the epicardium, the repolarization wavefront is coming from here towards the endocardium. So looking at the nature, when this was depolarization, this is repolarization. If this activity has to be shown from a different point of view, when repolarization is coming towards this side, it can be represented as depolarization going towards this side. Okay, it is the same activity. We can say that the depolarization is again going from endocardium to the epicardium. Try to imagine this thing, try to understand, try to absorb this information, and use your mental process of imagination to understand. For lead V1, what happens is we'll be looking at the heart from somewhere here, LV over RV. So it will be looking at somewhat this area of the heart. Major chunk will be this thick left ventricle, and the repolarization is going away. It means the depolarization, if we translate, is coming towards it. So this will be recording a positive deformation. With this, we understood why the direction of the T wave is in concordance with the QRS complex. So here we understood why the direction of the QRS complex and the T wave is concurrent. It is called as concurrent, or it is also called as concordance. Now we need to answer the second question: why the QRS is spiky wave, why the T wave is a smooth rounded shape wave. To understand that, this is slightly difficult for me to teach you in a depiction way by drawing things, but it is very easy once you start imagining and come in tune with me or start imagining the things. All of these epicardial cells will at once start to repolarize, then their subsequent cells will repolarize, then again their neighbor cells would repolarize, then after that these cells will repolarize, and this way the repolarization will occur subsequently in the entire left ventricle. So this is a very different process as compared to the depolarization, which was occurring from different points and then spreading in a spatial propagation way. The repolarization is happening in instantaneously in different cells, different cardiomyocytes, depending upon the length of their action potential in this way. So the net effect is that the activation is kind of moving from here towards here in a smooth way. It's not that this area first gets repolarization and then this area gets repolarization and then the basal areas get repolarized. It's not that way. The entire left ventricle from the epicardium towards the endocardium, they get repolarization because a large number of cells, the entire epicardial cells, they repolarize, and then their subsequently neighbors, they repolarize, and then subsequently their neighbors repolarize. It kind of creates voltage which is in the direction from the epicardium towards the endocardium. So for each and every lead, for example, if we talk about if we see our lead V1, we draw our ventricles, the repolarization is happening from here to here. That is, if we talk in terms of depolarization, that wavefront will be coming from here to here, okay, which will be coming right onto it, and V1 will be recording a positive deformation. At the same time, the lead V5, which is located here and looking at the heart from this direction, but this V5 will also have the wavefronts of repolarization going away. That is, the depolarization equivalents, they will be coming towards it, and it will be recording a positive deformation. In the same way, for lead 2, the long axis of the heart, the activity happening in this way, so the depolarization is coming in this way. So ultimately, for each and every lead, the activity will be coming towards them, and the voltage of this activity is again comparable to the explosion of a firecracker in a smooth fashion, and so it produces a smooth type of deformation on the baseline, isoelectric baseline. There is no fast conduction and large number of cardiomyocytes activating multiple wavefronts getting generated, which creates a very steep voltage, creating a gunshot like deformation on the isoelectric baseline. It is different, so it is just like the P wave, smooth activity creating this type of smooth wave, the T wave. So it was quite difficult to explain, and I think I have managed to explain you somehow. You look at the video a few times and try to imagine, go inside the phenomenons happening and try to imagine. I'm sure you'd be able to understand it yourself. So now we know the formation of the P wave, now we know the formation of the spiky QRS complex, and now we know the formation of the T wave. We also know the duration of the P wave is the time taken for the activation of complete left and right atria. We also know that the duration of the QRS complex is the time taken for the activation of the complete right plus left ventricle, and right from the beginning of the activation till the beginning of the T wave, the cardiomyocytes remain activated. That is, they remain in the plateau phase. And once their plateau phase ends, they start to repolarize. They repolarize in a fashion from epicardium towards the endocardium, which is essentially depolarization going from endocardium towards the epicardium, which we have seen in a directional vectorial point of view is coming towards the recording electrodes, and it gets recorded in the positive smooth shape waveform. And the duration of T wave is the duration required for the entire cardiomyocytes, the ventricular cardiomyocytes, to go from a depolarized plateau phase to the repolarized state. This is recorded here, and once this is recorded, then the isoelectric baseline remains.